Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much.
Thank the organisers for giving me the excuse to come back to Cambridge again. I'm always happy to do that. So this is joint work with Katerina Stroppel. We've actually written 5 BS papers on this subject now. Well, they're all available on the archive, so that I'll use those initials whenever I need to refer to one of these papers. So there aren't very many situations where you meet a highest weight category in representation theory which you can work out completely by hand. And we've been looking at one of those situations, and it's really a beautiful family of examples. So I just want to tell you about this family of examples again. So here's a little map for the talk. This family of examples really all stems from the Kazhdan-Lustig polynomials for Grassmannians. It's one of those very rare situations where Kazhdan-Lustig polynomials can be worked out explicitly by a closed formula. And in this case, the closed formula for the Kazhdan-Lustig polynomials for Grassmannians was worked out by Lascaux and Schutzenberger in 1981. And the combinatorics that they used to write their closed formula is sort of very Catalanish sort of combinatorics. It's kind of a fun combinatorial thing. And they get this beautiful closed formula for these Kazhdan-Lustig polynomials. So the family of kind of easy highest weight categories is all kind of linked to this nice family of Kazhdan-Lustig polynomials. So of course the first situation that these Kazhdan-Lustig polynomials show up are when you're looking at, and this is after all the Kazhdan-Lustig conjecture. So you look at parabolic category O, for the Lie algebra GL m plus n, and the parabolic whose Levy factor is GLM cross GLN, just corresponding to Grassmannians. So these parabolic Kazhdan-Lustig polynomials describe the decomposition numbers or the inverse decomposition numbers in this parabolic category. So this is, of course, the Kazhdan-Lustig conjecture, but I said that this highest weight category could be worked out explicitly by hand, and that in this case you don't need any geometry to get this connection. You can prove it just by very elementary methods, and in this case it was worked out in an elementary way after the Kazhdan-Lustig conjecture was proved in general, but the elementary proof for this Grassmannian case was worked out by Enright and Shelton. So that's what I mean by highest weight category being worked out by hand in that sort of sense. Another easy sort of situation in representation theory which you can work out by hand that kind of fits into this family, I'll just kind of very roughly write level 2 Hecke algebras. These are also controlled by exactly the same family of Kazhdan-Lustig polynomials. So by level 2 Hecke algebras, I mean, for example, Hecke algebras of type B, when the parameter, the little q, that's the long root parameter in the Hecke algebra, is generic. But the other parameter, the big Q, is chosen so that the algebra is probably not semi-simple. But I guess this would be, probably I should write a rekey for this. But again, the representation theory of these level 2 Hecke algebras is sort of, they're not semi-simple, but they're easy enough that you can work them out by hand and see this link to these Kazhdan-Lustig polynomials. Another situation which I like is the representation theory of the general linear supergroup, GLMN, just over the complex numbers, so just rational representations of this supergroup. And in that case, I worked that out about 10 years ago, and again, these same Kazhdan-Lustig polynomials show up when you work out this highest weight category by hand. And the subject of today's talk The fourth situation where exactly the same combinatorics kind of crops up, and you can see this all by hand. And at the combinatorial level, this connection with this walled Brauer algebra, which I'll tell you all about in a little while, the link between that and these same Cauchy-Listing polynomials was worked out by Cox and de Vischer. Only last year did they really fully work out that connection. So everything that I've written down here, I'm just writing down some kind of purely combinatorial statements. The combinatorics of all these sort of naturally occurring beasts in representation theory are all described by this family of Cauchy-Listing polynomials. So what we've been doing in the last few years in these BS papers is kind of upgrading these combinatorial coincidences here to equivalences of categories. So I'm just trying to fit it all into this blackboard. Maybe I can just do it. So actually there's a beautiful thing which I'll tell you about in a little bit, but it's a suitable generalization of Kovanov's arc algebra so I'll tell you about this in a little while, but this is a diagrammatically defined algebra which is sort of an algebra which is based on this same Catalanish combinatorics that appears in these Cauchy-Listing polynomial formulas. This is an algebra built out of that combinatorics. And we found that the category of finite dimensional modules over the appropriate one of these algebras is equivalent. You have to, of course, pick the suitable generalization depending on which situation you're looking at, but we found that it's equivalent to all of these different algebras or categories there in representation theory. And let me just kind of put in a few names here. So this is kind of the first one, the most important one, which everything kind of stems from, this category O for Grassmannians. And in this case, of course, the regular block of this category O for Grassmannians, it's the same by the localization theorem as looking at perverse sheaves on Grassmannians. And Braden studied the category of perverse sheaves on Grassmannians and found an explicit presentation for it. And using that, Kovanov and Stropel were able to make a connection, a direct connection between this perverse sheaves on Grassmannians or this corresponding category O and some sort of arc algebra, this thing I haven't told you about yet. So this was via perverse sheaves. And then in our paper 3, we kind of redid this connection and explained this connection kind of in an elementary algebraic way. These suitable generalizations of Kovanov's arc algebras, that was what our first two papers were all about. We were defining these algebras and studying their basic properties just in a self-contained way. So that's that first connection, that first equivalence of categories. This second one was also sitting inside BS3. And then this one, the fact that the rational representations of the general linear supergroup is related to some variation of Kovanov's arc algebra. That's exactly what I spoke about at the last talk I gave in this room. And of course, you can go and look at the video online to find out all about that. And then our new paper is this final link between the arc algebra and the walled Brauer algebra. And of course, that's what I'm talking about today. So that's the map. Actually, before I move on and start actually talking about these two algebras and explaining the connection between them, I just wanted to mutter something about there being a kind of a folded version of this whole story. So there's another family of Cauchy-Listing polynomials which have a closed formula, much the same spirit as Lascaux, Schutz, and Berger. And those are the Cauchy-Listing polynomials attached to the other families of Hermitian symmetric pairs. So I'm talking about the ones in the other classical groups. So there are four other situations. Bn minus 1 in Bn, An minus 1 in Cn, An minus 1 in Dn, and Dn minus 1 in Dn. And of those, actually two of them are kind of almost trivial, but the other two have an explicit combinatorial description worked out by Brian Bowe in the 80s. And the combinatorics looks much like this sort of Catalanish combinatorics of Lascaux and Schutzenberger, but it's sort of the diagrams are all folded. And of course, by the Cash-Analytic conjecture or Enright and Shelton, that combinatorics controls the corresponding category O for the corresponding complexified emission symmetric pair. And it looks now, there's kind of enough evidence coming in on a combinatorial side that actually everything in this picture has an analog in that kind of folded world. Here it would be some sort of cyclotomic BMW algebra. Here it's going to be the orthosymplectic supergroup. And here, rather than the Wald-Brauer algebra, it's actually going to be the classical Brauer algebra. And finally, at the bottom, my co-author Katerina has told me now that she's worked out how to define a sort of folded version of this arc algebra. And so all the ingredients exist, all the combinatorics exists, and you know it's a huge project. But I think slowly this picture is being developed also in this sort of folded world. It looks like it's going to be 4 or 8 times harder, but this is a beginning. So those of you who like Brauer algebras, this Wald-Brauer algebra case is sort of a beginning to set the scene for this. All right, so that's the map. Let me now try and actually tell you something a bit more precise. So let me start off by trying to be a bit more precise about what these generalized arc algebras are. So this is a very sort of explicit piece of this kind of diagrammatical algebra, and the diagrams are just built from this Catalan type combinatorics that I've already talked about quite a lot. So let me try and give you a sketch of this. So what I need to do is to fix a set, I'll call it a good set, of what I'll call weight diagrams. So what's a weight diagram? Well, a weight diagram, it's a horizontal axis with vertices at all the integers, and all those vertices are labeled by one of the 4 symbols, 0, cross, up, or down. Maybe you can't see that, 0, cross, up, or down. And then there's some finite conditions, so a number, let me give you an example of a weight diagram. So it's just a number line, and there's vertices at all integers, and all those integers are labeled by some of these symbols. So there might be all zeros to the left there. I think I had a particular example in mind. There might be some ups or some crosses, some downs. What was I going to do? It doesn't really matter. Maybe all up to the right. So that's an example of one of these weight diagrams. So there's some finiteness condition that outside a finite subset, outside a finite interval, you can't find an up to the left of a down. So after throwing away finitely many of the vertices, you can't find an up to the left of a down. So that's just a technical assumption. So let me call my good set of weight diagrams something, I'll call it lambda, capital lambda, for some good set of weight diagrams. So these are kind of very daft combinatorial things, just these ups and downs is really all that's important. And then there's a Brauer order on these weight diagrams, and it's just generated by down, up is less than or equal to up, down. So that's the basic move that generates the partial order that I'll call the Brauer order. Just flipping an up-down pair. Flipping an up-down pair. If the downs move to the right, the weight diagram gets bigger in the Brauer order. And I'll write twiddles for the corresponding equivalence relation. Just the transitive closure of the Brauer ordering. So this relation twiddle, it's just permuting ups and downs. 2 weights are equivalent if you can get one from the other by permuting ups and downs. And here when I say good set, I just mean closed under that relation twiddles. So once you've got one of these good sets of weight diagrams, the arc algebra, I'll just call it K. Of course, it depends on that fixed set lambda of weight diagrams. It's just the associative C algebra with basis given by a bunch of explicit diagrams. And I'm going to just kind of write these diagrams in a slightly funny way. I'm trying to draw a picture of a diagram here. So this is what all these diagrams are going to look like, and I'll tell you what this means in a minute, as lambda runs over the whole set of all of those weights in the given set lambda. So what is this diagram A lambda B meant to look like? So you start with your weight diagram lambda in the middle, and then underneath you glue cups like that to the vertices and raise down to infinity like that to all the vertices, so that these endpoints are exactly all the vertices labeled up or down. You don't glue anything to the vertices labeled naught or cross. They're just kind of dummy vertices that are just carrying some extra data. And the way you have to do this so that there are no crossings. Each cup has one up and one down, labeling it. So if you think of those ups and downs as kind of arrows, each of the cups becomes either clockwise or anti-clockwise in this diagram. And all the up rays are to the left of all the down rays. Those are kind of a bunch of strange looking rules. So that's the sort of diagram you put underneath. So let me just give you an example here. If this is our weight lambda, let me put one of these, let me close this up underneath by these cups and rays. So I can do, I can put like a cup there and a cup there, a cup there. I could not do this, for example, because that's a ray pointing down to the left of a ray pointing up. All the up rays have to be to the left of all the down rays. So I have to close it up something like that. And then all these other verses, I can have infinitely many rays here. And I should have said finitely many cups. An extra little finite exclamation. So,
John, there's some ups you can connect anything.
did I miss some?
On the far left.
Oh, I didn't see them. Good. That's easily fixed. There you go. Okay? So that's what the diagram A looks like, and the diagram B is exactly the same sort of thing, except now you're gluing caps and rays up to infinity with the same rules. So let me just kind of do that. Let's close it at the top. Can I think of an interesting way to do it? Something like this. It's always hard to see these diagrams when you're standing here. Let me see, I want to just do that there. I can't really think of a very exciting way. Why am I struggling? Let me try and do something sensible. Got to do these all the way over, something like that. Oh, I wish I wanted a better example where I could show you something interesting where you get this sort of funny thing happening. So that'll do. I mean, it's not important. That's an example of one of these. I changed my lambda. I cheated a little bit, but there's an example. Okay. So some very, very explicit set of diagrams give a basis for this algebra K lambda. And then the multiplication is an explicit combinatorial procedure. So the way you multiply two of these diagrams, let me just give you a slightly sketchy picture of the multiplication. Let me take two such diagrams, A lambda B and C mu D. The way you multiply them to get a new sum of diagrams, well, the product's often 0, is 0 unless lambda and mu are in the same equivalence class under this relation twiddle, and B and C are mirror images. So now assume that lambda is in the same equivalence class of mu and that B and C are mirror images. Then the way you compute this product is you just stack diagrams, maybe stack diagrams properly, A lambda B, C mu D. And this assumption about B and C being mirror image pairs means that in this middle bit of the diagram, everything's kind of symmetric. So whenever you have a ray pointing up in B, you have a ray pointing down in C. So then you just join rays in this middle part, and then you smooth out BC. So now I decided I wasn't going to actually go into the details of this smoothing process for you because it's a little bit technical, but it's kind of the most beautiful part. So it's a shame I decided to skip it. But I'm going to refer you to BS1 for the details of this smoothing process. You kind of smooth this out until you just have lines going straight through, and then you collapse. So this is the most beautiful part, which maybe I just say enough to whet your appetite, so maybe you do look here. The key ingredient in the smoothing construction is the TQFT for the cohomology of P1, and that's the key idea of Kovanov, why these are Kovanov's arc algebras, that smoothing procedure. It's really quite ingenious and quite beautiful how it works. So what happens when you do this, when you smooth out B and C and then contract at the end, you always get at the end some linear combination of diagrams of the form A nu D. So you always have this A at the bottom stays and this D at the top stays, but this smoothing can kind of change these weights a little bit, and you can actually get a sum of new diagrams in this process. So that's kind of a slightly skimpy account of how this diagram is defined, but I want to whet your appetite for it now by telling you about its properties rather than its actual definition. So this algebra K is positively graded. Actually, the basis is just a homogeneous basis, and the degree of a basis vector is the number of clockwise cups and caps. So once it's positively graded, I should tell you about the degree 0 part. And the degree 0 part has a basis of orthogonal idempotence. So E lambda here, the idempotent index by lambda, is the unique diagram A lambda B with the weight lambda labeling the axis that's of degree 0. Degree 0 means only anti-clockwise cups and caps. So it's an easy thing to ponder for yourself if you have one of these weight diagrams. There's a unique way to close it underneath and on top using only anti-clockwise cups and caps to satisfy the rules of these diagrams. Then that basis vector, that's the thing I call E lambda, and it's actually an idempotent. So that implies that the simple K modules are all one-dimensional. I will just denote them by L of lambda. They're just K0 over K, sorry, K over K greater than 0 E lambda. So just take the left ideal generated by the idempotent E lambda and just throw away all the stuff of positive degree in there. That gives you this one-dimensional representation just spanned by the image of the idempotent E lambda, and those are all the simple modules for this. The Jacobson radical is just all the strictly positive degree stuff in this algebra. So this is a basic algebra. The simples are all one-dimensional. They're labeled by this set of weight diagrams that we started with. This algebra is quasi-hereditary. In fact, the basis is what's called a cellular basis, something introduced by Graham and Lehrer. And so this gives you some, I'll just call them standard modules. They're standard modules of the quasi-hereditary algebra, or cell modules from the cellular basis. I'll denote them V of lambda, lambda and lambda. And once you have a cellular basis, everything is combinatorial in nature. You get an explicit basis for these standard modules. They just have a basis consisting of diagrams. Well, they just look like half of the diagrams that give a basis for the original algebra. So I only need the A part and the weight lambda, not the B part. So I only need the cups. So let me kind of, I don't know, denote it something like that. So lambda's fixed. Then V lambda has bases consisting of all these ways of closing lambda underneath with these cups following the same rules. Now, once I've got a basis, the way the algebra acts is just the same. You just stick your vector, one of your basis vectors for the algebra just underneath, and you do the smoothing process again. So it's totally explicit. But because all the simples are one-dimensional, having a basis for the standard modules is essentially, if you look at it a little bit, it's really actually it's already a composition series. One-dimensional simple modules, the basis vectors actually already kind of give you very easily all the composition factors. Of the standard modules. Everything's on a plate in this thing. It's this sort of basic diagrammatic algebra. I should just tell you that one of these basis vectors here, A lambda inside V lambda, it corresponds to some composition factor. Did I name those simple modules over there? Yes, L. It gives you a composition factor L mu, where mu is obtained from lambda by flipping all the labels on all the clockwise cups. So you just look at this diagram here. You have this basis vector in the standard module. There might be some clockwise cups in there. You just flip all the orientations of all of them. This weight lambda at the top changes into a new weight mu. That's the L of mu that basis vector spans in a composition series for the standard module. So I'm just trying to say enough to really convince you that this diagram algebra, it's just totally explicit combinatorics just sitting in front of you. Of course, you have to think about the combinatorics of these strange cup diagrams here, but that's the Catalan combinatorics that I've talked about a little bit. So just looking at cell modules kind of cuts in half, and you just see the Catalan combinatorics coming here. Okay, a little bit more. Where's the eraser? There's one down here. No, just do that. Maybe the blocks. Well, I already had my equivalence relation twiddles. The equivalence classes under this relation twiddle, they're exactly the blocks of this algebra. K is positively graded. The degree 0 part is semi-simple. It's just a direct sum of copies of the field labeled by the weights, those idempotents. In fact, K is a Koszul algebra. And the point really of that statement is you can actually prove this just directly, just in the same way that I calculated composition multiplicities of standard modules directly there. You can actually explicitly write down linear projective resolutions of these standard modules to prove that the standard modules are Koszul. And again, you can just read this off. You read off the Koszulity polynomials. Of course, you get in the end the Koszulity polynomials for Grassmannians when you write down these resolutions. Everything is totally explicit. And this is, of course, not so surprising, because I told you that one of these things was exactly parabolic category O for GLM plus N, GLM, GLN, and you knew everything along those lines for this thing already because of Koszulity conjecture and subsequent work of Beilinson, Ginsburg, and Zergel. The grading here, the Koszulity here, translates exactly into the known grading on parabolic category O, the known Koszulity on parabolic category O from Beilinson, Ginsburg, and Zergel. The grading here, well, I'm skipping ahead maybe a little bit, a tiny bit more. So these algebras K, these arc algebras, they're kind of really remarkable. They're the most beautiful example of all these nice quasi-hereditariness, Koszulity, and representation theory, very explicit ones that you can work out. And if you look at the blocks, there are sort of various basic types. There's the types where you have finitely many ups and downs in the diagrams, say m ups and n downs. That's exactly this situation here, where you get, in that case, you would get a regular block of parabolic category O. Right? So when things are finite, both ups and downs are finite, that's this situation. But there are also situations where you have finitely many ups and infinitely many downs, and these algebras K still have all the properties that I just said, but it happens now that the blocks become infinite dimensional now. So when I said these were quasi-hereditary, in those cases I mean a slight generalization of that, but a natural generalization. And that's exactly the cases that come from GLMN, the supergroup GLMN. So this is kind of a weird case, because if you look at the Brauer order, you have infinite chains in the Brauer order, both above and below. So sort of that's something that is kind of nice to deal with these examples, but in general quite a weird phenomenon. And then the other situations where you have infinitely many ups and infinitely many downs, and when we were writing our first two papers, we included this just for the hell of it, because we could, but we didn't see any chance that these were going to be natural in any way. For example, in this case, actually, even the cell modules turn out to be infinite dimensional. So the standard modules have infinite length in this case. So things aren't even Artinian. And so we're kind of well away, actually, from the honest notion of quasi-hereditary or highest weight category, where Artinian is usually a hypothesis. But still, everything works. You can make sense of all of the things that I've said. So it came as a shock when actually suddenly we found that this infinite case did indeed appear in nature. And that's what I'm going to tell you about with these Brauer. So it's a kind of weird situation. Actually, the chains in the Brauer order are all bounded above, but infinite below. So something kind of slightly strange happens in this case. Okay. Well, okay, so I've tried to say a little bit about the arc algebra. I kind of skipped the main thing, telling you really what it was, but maybe one person might look. It's a beautiful, beautiful definition, the actual smoothing procedure based on this TQFT. It's really neat and certainly not obvious. Okay, so I guess now we should go to this Brauer algebra. you know what we're doing because I've shown you the map. I've told you about the arc algebra, now I've got to tell you about the Wald-Brauer algebra, and then the theorem will be that they're Morita equivalent, suitably adjusted. So let's move on and start again a little bit with this Wald-Brauer algebra. So for this I need integers r and s greater or equal to 0 and a parameter delta. And then this Wald-Brauer algebra, actually I think it was first studied by Turayev in the late 80s. So it's not nearly as classical as the Brauer algebra itself, but it's actually a subalgebra of the classical Brauer algebra. And again, it's a sort of diagrammatically defined algebra, but of a very different sort of spirit to this arc algebra that I just defined. But it has basis of diagrams. The sort of diagrams you get in this Wald-Brauer algebra. I want to have some dots. I want to have R black dots and S white dots at the top and at the bottom. And then you put inside a matching between these dots, just as if I was drawing a permutation or something like that diagrammatically. Here you put in a matching. So the rule is that, well, let me give you a matching. I don't know, there's some sort of matching. You can match dots at the top with dots at the top. So this is a horizontal strand here. You can have horizontal strands, something like that. There's a matching. Okay, crossings are allowed now. It's quite different. We started again from before. But there's a rule. Horizontal strands like this one, as a horizontal strand matching two dots on the same horizontal axis, must be different colors. And vertical strands must be the same color. Okay, so there's an example of one of these Wald-Brauer diagrams you can see. Okay? And then the multiplication is just like the multiplication in the Brauer algebra. Here I really can tell you honestly the multiplication. You just concatenate your diagrams vertically. Concatenate vertically. You just stack one diagram on top of the other. But when you do that, you might get some internal circles produced when a cup and a cap kind of go together inside. So then you have to delete the internal circles and you times by delta each time. So each internal circle contributes a multiplicative factor of delta out the front of your diagram. So hopefully that's familiar. I'm sure people have seen the Brauer algebra before. So I just need to tell you a tiny bit about the representation theory of these Brauer algebras. It's not terribly difficult to show. You need to work everything out about it when delta is not an integer. This is a semi-simple algebra. And for many applications, that's kind of the most interesting situation, but it's exactly not the situation I'm looking at here. I want these algebras to be non-semi-simple. So let's assume from now on that that parameter delta is actually an integer. They're still semi-simple if delta is really big or really negative, but small deltas, these algebras now can fail to be semi-simple algebras. So the interesting representations of these Wald-Brauer algebras are labeled by bipartitions. So I'm now going to let my capital lambda just be the set of all bipartitions. And let me let lambda Rs be the bipartitions such that the size of the left, the first one of that pair of partitions is R minus T, and the size of the second one of that pair of partitions is S minus T for some T. And then for each of these lambdas in the set lambda Rs, there's a corresponding module called C of lambda, which is called the cell module for the Wald-Brauer algebra. And it's a cute definition. It's easy to tell you what it is. So as a vector space, this cell module looks like the direct sum over rule V okay, maybe I said it was cute and I've written something that looks a little awful. What have I got here? This in here is the classical spect module for the symmetric group, sigma R minus T cross sigma S minus T. This is just an outer product of two spec modules for those two symmetric groups. And then this is just a direct sum of copies of that vector space, and out the front these vectors indexing the copies are actually diagrams of this form. Where you have R minus T black dots at the top, S minus T white dots, R black dots at the bottom, and S white dots at the bottom. So you take the direct, so this V ranges over all these sorts of Wald-Brauer diagrams. And then you have some vertical strands and horizontal strands at the top as before. But I've got fewer dots at the top now. I don't allow any horizontal strands at the top, only T horizontal strands at the bottom. And all the vertical strands, there have to be no crossings of vertical strands. And then the way the Wald-Brauer algebra acts, you take a Wald-Brauer diagram, you just stick it underneath. If you get internal circles, you just remove them and get a multiplicative factor of delta as before. And then, but when you do that, you might get vertical strands that cross. So you do that, and then you have to propagate those crossings of vertical strands upwards, and you get a little permutation in that symmetric group popping out at the top. You just act with that on that spec module for the symmetric group. That maybe makes sense. It's a very, very explicit defined module. It's really some sort of induced module in a suitable way. So generically, these cell modules are irreducible, and they give you all irreducible representations up to isomorphism. So this is kind of all well-known, sort of pretty standard stuff about these Wald-Brauer algebras. And the last ingredient, I need to define one more set, lambda Rs with a dot on the top. So this is almost the same set of bipartitions that I had before, but occasionally you need to throw away the empty bipartition. You throw that away if R equals S is bigger than 0 and delta is 0. Otherwise, the dot doesn't mean anything. Okay, so this is only if delta equals 0 if you've got to do anything here at all. If delta's non-zero, then nothing going on. Then if lambda is in this set, lambda Rs dot, the cell module has simple head always which I'll denote d of lambda, and these give all the irreducible representations, even in the non-semi-simple case. This is a sort of very familiar sort of picture. So this set lambda RS with a dot on naturally labels the simple modules for these Wald-Brauer algebras. Okay, so now we can finally tie this thing up. So I've got my set, capital lambda, of all bipartitions, and now I just need to tell you how to view that set instead as a good set of weight diagrams that we had when we were talking about the arc algebra. So I'm going to identify lambda in lambda RS with a weight diagram So what I do is I let I up, so this is going to index where I put the label up on my weight diagram. So this is the left partition. So lambda L1, that's the first part of the left partition in that bipartition. Lambda L2, that's the second part in the left partition of that bipartition. You need to shift to get a strictly so the parts were weakly decreasing. You need these shifts in here to get a strictly decreasing sequence, so that none of these things are equal. And you let I up be, so this is where delta comes in. Okay, so the parameter delta, the integer delta, comes into this definition right here. So I up, but it's just coming from the right partition, the parts of the right partition, but negated, and there's these shifts. Then oh golly, that was meant to be a down there. Sorry, thank you. So then you put the symbol up at all the vertices in I up, the symbol down at the vertices in I down, and if you have a vertex with neither of those labels, you put the symbol naught, and if you have a vertex with both those labels, well, that's an up and a down. That's the symbol cross. Okay, so that's the little weight dictionary to view this set of bipartitions as Wald-Brauer diagrams. Let me just do one example. Well, I'm going to do the trivial example, but you'll see the sense of these diagrams then. The empty bipartition under this dictionary, you have all ups. That set I up will be 0, -1, -2, and so on. So you have all ups to the left here. And that set I down is 1 minus delta, 2 minus delta, and so on. So you have all downs from there onwards. And if we assume that, say, delta is less than or equal to 0, then in between you'll have some noughts, something like that. That's what the weight diagram of the empty bipartition looks like. And then what's going on is if you have a different bipartition, so there's some lambda L here, that's just promoting these ups. It's kind of bumping the ups to the right according to the parts of lambda L, and is demoting these downs, is bumping the downs to the left according to the parts of lambda R. So it's kind of a simple thing. Okay, so now it's all in place that I can state the main theorem. Well, you know the main theorem already probably, but now I've got the technical details in place. So the Wald-Brauer algebra BRS delta is Morita equivalent to the algebra EKE for lambda as above. So K is this Kovanov algebra K lambda for exactly this good set of weight diagrams that I've just defined. But you see, it's not the whole Kovanov arc algebra K. This was this case where, look, there's infinitely many ups and there's infinitely many downs. It was this kind of bad case that wasn't even Artinian. It's not that, it's a truncation of that, EKE. E is just the idempotent, the sum of the weight idempotents E lambda that we had in the arc algebra, indexed by that set lambda RS dot here. So this is a finite set here. So we're sort of we're taking this rather scarily big but kind of morally quasi-hereditary algebra K with a big infinite weight poset, and then we're truncating it down to a finite set of weights. Actually, it's a very nice and natural truncation. At least if I assume that this funny case delta equals 0 when this dot had some meaning possibly, if we ignore that case, then lambda RS is an upper set in the poset lambda, and truncating quasi-hereditary algebras in this way with respect to upper sets is a very nice operation. So in that case, EKE is quasi-hereditary again. And Koszul again, it's actually standard Koszul again. So that truncation is very good, except in this sort of slightly funny case when delta is 0. Hence, the Wall-Brauer algebra is Morita equivalent to a Koszul algebra, a finite dimensional Koszul algebra. In these cases. And of course, that was kind of the whole point of why we wanted to do this in the first place. Maybe I could just say one more thing about this Morita equivalence. Under the equivalence, the standard modules correspond to the cell modules. That's why I bothered to define them. So of course, the simple modules correspond to the simple modules. So things like the known combinatorics of decomposing cell modules into simple modules, which Cox and de Vischer worked out, it's immediate from the combinatorics of these arc algebras in this Morita equivalence. And all the other kind of things, the calculations of Cauchy-Stanistic polynomials and so on for these Wall-Brauer algebras, it all falls out then from this general theory of these arc algebras. Okay, so I just want to finish with a conjecture. Well, maybe I should say a little bit. I'm not going to explain the proof, but the idea of the proof is very simple, and I can tell you in 1 minute. Just pick integers m and n with m minus n equal to delta, and look at the general linear supergroup with an actual module V. And then, and this is really where these Wall-Brauer algebras arise in nature, you look at this mixed tensor space. So R copies of V and S copies of the dual V star, and you ponder the endomorphism algebra of mixed tensor space for the general linear supergroup. And it's not too hard to see the Wall-Brauer algebra acts naturally on here. I won't go into the detail, but it's easy to cook up an action. And so what the first thing we show, it should be known long ago, but I couldn't find it anywhere, is that if R plus S is less than M plus 1, N plus 1, this is an isomorphism. Yeah. Okay, so providing you pick M and N big enough, you can always do that so that this holds, then you get a very explicit realization of these Wald-Brauer algebras. They are exactly endomorphism algebras of GLMN on mixed tensor space. And so then what we do is we study these endomorphism algebras. And how do we study them? Well, this is the general linear supergroup for which in BS4, the previous talk, you were all there, we developed this combinatorial theory of arc algebras for GLMN. So we just plug in to that combinatorial theory at that point and we recalculate this endomorphism algebra via the equivalence of categories in BS4, and out pops this crazy diagrammatic algebra, this kind of graded version of the Wald-Brauer algebra. And that's sufficiently nice that we can then see that that's Morita equivalent to this basic algebra up here. So it's, it's a sort of big machine that we just plug into. But it all depends on picking an M and an N. We just pick a very big M and N so this is true and go ahead. But at the moment we can't see that the Morita equivalence we end up constructing is independent of the choice of M and N. And this is very annoying. It means that I have to state a conjecture rather than being able to give the talk that you really want to give. So let me just finish with the conjecture, just briefly. So actually, rather than looking at the Wald-Brauer algebra, it's actually more natural to look at something called the Wald-Brauer category. So the objects are finite sequences of black dots and white dots. And morphisms between two such sequences, you have one such sequence, any order, any number, I don't know, are C linear combinations of those Wald-Brauer diagrams. That we had before. Okay, so this is I was already doing this earlier on by accident. This is very natural to just allow some variation of numbers and places of black and white dots. This is even a tensor category. This is kind of a familiar thing. The tensor product is just horizontal concatenation of diagrams. In fact, this tensor category, this Wald-Brauer category, it's just the free tensor category generated by one object of dimension delta and its dual. So the one object is the black dot, its dual is the white dot. Okay. So this is kind of very natural, but it's not a. Then people normally pass to this category, which they call rep GL delta, whose definition has its origins in work of Deligne, who did this for the symmetric group, I think. So this is, you take this, I call it B of delta, this thing, and you take its additive envelope and then its Karoubi envelope, so the idempotent completion there, to get this, it's still a tensor category. That's Deligne's category rep GL delta. So delta here might be negative, for example. This all makes sense even if delta is a complex number. This is kind of an interesting beast. But actually, again, this category is semi-simple unless delta is an integer. And so the conjecture, so this thing is sort of doing the Wald-Brauer algebras all together. Not just picking one of them and just studying one of them. One Wald-Brauer algebra is just one endomorphism space between one object in this Wald-Brauer category, but doing them all together and looking at all maps between them. When you do that, you get this tensor structure showing up, which is cute. So the conjecture, the thing we really wanted to prove, but still can't, is that this Deligne's category is equivalent like the K that I had before, right? I had this K where I viewed the set of bipartitions as a set of weight diagrams with a weight dictionary that involved delta. I don't mean K, I mean finitely generated projective K modules. So I get an additive category there. And so this, the theorem that I stated before is, this is the exact analog of the theorem that I stated before, that Morita theorem that I stated before, when you replace the Wall-Brauer algebra by the Wall-Brauer category, or rather this Karoubi envelope here. And, we ought to be able to prove it, but unfortunately, I mean, it's sort of this, we need to let M and N go to infinity here. We sort of need to do all the Wall-Brauer algebras at once. And because of this annoying little issue that we can't prove independence of M and N here, we can't take any limits in our arguments. And so at the moment we can't get here. Okay, I'll stop there, thank you.
Thanks very much. Any questions? Comments?
Say one additional thing you could do in this Hermitian symmetric cases was to calculate extensions between Verma modules. Can the same thing sort of be? Can this be seen?
Have you not asked Katerina this question? She has a student who was looking at exactly that, and in this type A world, can give some new formulas for extensions between Verma modules. So you know who to ask. I mean, she's calculating some quivers, for example, but they're complicated. So it's not totally satisfactory, but at least it's possible. This is a very special case, of course.
Do you think that your folded
Not mine.
yours and
My
Katerina,
co-authors.
will you be able to use that to prove the orthosymplectic conjectured Servile duality with the Brauer algebra?
Right. I mean, somehow it's a whole. You have to build the whole picture. I think the expectation is that this orthosymplectic supergroup will be one sort of Servile duality with this folded diagram algebra, and then there'll be another equivalence, another sort of Servile duality from that to this category O or the Brauer algebra.
And your second type of basic type, sort of slightly infinite, is that pseudo-compact quasi-hereditary? Is that the definition?
No, I don't take any kind of topological completions. I just always work with this. These are all for me just locally unital algebras. They're not unital algebras.
And is there an analog of cellular in that setting? An obvious.
In the locally unital setting, yeah, you can write down. It's not really a big deal. I mean, a big help here is we have this grading, and all the graded pieces are finite dimensional. So, you know, the algebra might be infinite dimensional, but it's not really. The graded pieces are finite dimensional.
Further questions, comments? Thanks very much.